chapter that we're going to go into, and remember looking forward a little bit, is it March 7th or 6th? I can never remember the date. What's the day we're having the test? Is it the 7th? Okay. March 7th, we're having test 2, excuse me, which is covering chapters 4, 5, and 6, okay? Sorry. That's a lot of material, because of chapter 4, we had all the different kinds of reactions, being able to do ion exchange and redox and all of that kind of stuff. Then we ended with concentrations and stoichiometry using concentrations, right? Then all of the chapter 5 stuff with thermodynamics, okay? And then chapter 6, we're going to be starting into something called quantum mechanics, all right? Now, you're making a face already. You must have heard about quantum mechanics. The good news is that we are not going into the detail on quantum mechanics that gets it really scary and obnoxious and everything like that. The bad news is it's still quantum mechanics. There is a certain amount that the math is a little bit weird, what it predicts is a little bit weird. Have you guys, I almost hate to say this, does anyone in here like Big Bang Theory? The show? Okay. Do you know when they talk about Schrödinger's cat? That's quantum mechanics, okay? So that's where we're headed, is some of these weird predictions of Schrödinger's cat and stuff like that, okay? It is kind of an exciting topic, but it's also a rather strange topic because it's treating things at every particle is not just a particle, it's also a wave. It always has a dual function, okay? Which means that we need to talk a little bit about waves first. All right, that's where we're going to start, is talking about waves. And we'll start with talking about light waves because they're a little bit easier, because light, for the most part, has very little particle character. It actually does have just a little bit of particle character. But for the most part, it's a simple wave, and we can do calculations as if it were a simple wave. Okay, and that's where we're going to start with some things. I did want to mention one thing, I almost forgot to. On page 202, you don't need to turn there necessarily, but you might want to make note of it. At the end of most of these chapters that we're getting into a little bit more with math and stuff like that, they give you a page of key equations. That's to remind you of all the stuff we did in the chapter, because sometimes it's lots of stuff. So the end of chapter 5, which would be page 202, is the page of key equations. It gives you the equations. It gives you a very short definition of each one of these equations. They're pretty short definitions. But you should be aware of those equations. Those are the kinds of things you want to put on your 3x5 card, because a lot of times the calculation isn't difficult if you have the equations, but you need the equations. Okay, so at the end of each of these chapters that we get to, chapter 6 is going to have a lot of them. You're going to want to look at the page of key equations. Make sure you have those on your 3x5 card and that you understand how to use them. For example, if there's constants on there, we're going to be talking about Planck's constant in just a minute. If there's constants on there, you need those constants on your 3x5 card so that you know how to stick them into the equation, right? So that's kind of a good way to go back, review the chapter, just looking at the equations and saying, do I remember what that equation did, what the constants are, how I plug things in, etc. All right? So that's at the end of every chapter. Make sure you know what those are, okay? Now we're also going to have, as we get into some of these things, again, if you have the end of your book, at the very end of your book, you have some constants, okay? Some different things like, for example, the mass of an electron or the mass of a neutron, okay? Those are at the very, very back end of your book. We're going to need some of those as well, all right? So as we go through some of these calculations, you're going to need to be able to flip back to that page, all right? most constants you need to put on your 3x5 card, all right? That doesn't mean copy, there's 2 pages. Don't copy the whole thing and shrink it down. Look at what we're covering in the chapters. What constants are we using? And put those on the 3x5 card for that test, okay? All right, so having said that, let's go into chapter 6 and talk a little bit about waves and how waves work, okay? First of all, we're going to be referring to light, and so the light spectrum is on page 215, okay? So, when we're talking about a wave, you have a pattern like this, okay, where this is its wavelength, all right? So from the neutral point through the high, through the low, back to neutral, that is one wavelength. And we usually use the symbol lambda to represent wavelength.
Is that also the period?
The period is a little bit different. We're actually going to talk about frequency, which is an italicized V, okay? And it is related to wavelength, but they're actually inversely proportional, right? Inversely proportional. So let's think about that for a second. Now, it's a little bit harder to talk about things like sound waves or light waves because we can't see them. But most of you have probably experienced a water wave, like standing on a beach or something. All right, so you're standing on the beach, the waves are coming in. The longer the wavelength, the slower they come in, right? The longer the wavelength, the slower they come in. And that's what we mean by inversely proportional. Okay, if you have a really big wavelength, then make sure I say this correctly. If I have a spectrum, right, and these are my long waves, and these are my short waves, okay, then the frequency, and we usually get that in hertz. Hertz is 1/2, right? The frequency is going to be inversely proportional. The longer the wave, the slower it comes in, okay? Shorter the wave, the faster it comes in. Does that make sense?
The amplitude of it? Or
No, amplitude is this, the height, all right? This is the length, and it's an actual distance. Like, for example, if I'm talking about a water wave, maybe it has a wavelength of 10 feet. Okay, so it will come in at a particular rate, okay, per second. How many waves come in per second, all right? If it's 10 feet long, then you're going to have, let's say they come in at 10 waves per second, just to pick random numbers, okay? So 10 waves, that's pretty fast for water. Maybe we should say 1 wave per second. So 1 wave per second comes in with the water, right? Then if the wavelength is only 1 foot long rather than 10 feet, then we would get 10 times more waves coming in, wouldn't we? Yeah.
And you said something about hertz?
Hertz, which is Hz, is equal to 1/second. That's also written as seconds to the -1. Okay, that's the unit that we'll use for frequency. The units that we will use for wavelengths, if we're using standard units, will be in meters. A lot of times when we talk about visible light, if this was light spectrum, so that the visible light is in here, visible light is in the range of nanometers. Do you remember what a nano is? 10 to the -9th, right? 10 to the -9th meters. Okay, so a lot of times they will give wavelengths in nanometers or sometimes even picometers. Okay, because they're often very, very short when you're talking about electromagnetic radiation. Okay,